This video is about the topic Le Chatelier's principle, or I think you're supposed to pronounce his name Le Chatelier's principle. So Le Chatelier is shown here. I think his first name is Henri. He's a Frenchman. So Le Chatelier's principle states that when a stress is applied to a system at equilibrium, the equilibrium will shift in whichever direction reduces the impact of the applied stress. So we should talk about what stress means. First, though, let's put what Chemistry Cat thinks Le Chatelier's principle says. Reducing stress of chemical systems, increasing stress of chemistry students. Ha 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 ha. There's Chemistry Cat. Sorry. He's pretty cool. I like his bow tie. All right. Go back to the real Le Chatelier's principle. Let's talk about what stress means. Okay, so stress can be anything that disrupts the equilibrium, right? So remember that when we have a reaction, it comes to equilibrium and it has a set amount of product and reactant present in the same reaction vessel. And so if we add or remove reaction components, whether it's the reactants or the products, then that will certainly change the value for Q, right, the reaction quotient, and that means that you are no longer at equilibrium. So if you establish an equilibrium where Q equals K, then that means that if you change Q, then you're no longer at equilibrium because Q is no longer equal to K. So that's another way of saying if you add or remove reaction components, that will shift the equilibrium, and that's considered a stress. So adding or removing reaction components is a stress. Another way of influencing the equilibrium of the system, the equilibrium position, another stressor is the temperature. So if you increase or decrease the temperature by adding or removing heat, then that is a stress. Another stressor is increasing or decreasing the pressure of the system. Though all three of these can influence the position of the equilibrium here. So let's just willy-nilly crazy add some nitrogen. What that's going to do is it's going to disrupt the equilibrium. It's going to want to shift to remove what you added. And the way it would shift to remove what you added is to the right, because that will remove N2 by reacting it to form NH3. So that's going to shift to the right. It's going to consume hydrogen and nitrogen to form ammonia. And then we establish a new equilibrium. So another popular way of showing Le Chatelier's principle is using a balance, like a balance beam kind of thing, or something like this where you have this fulcrum in the middle and you have reactants on one side and products on the other side. And once they're at equilibrium, you can think about that as sort of being balanced, right? Equilibrium is a balance. And so if you add more reactants on the left, then what that's going to do is it's going to shift that equilibrium so that it's no longer balanced, and it's going to want to remove those things that you added, so the reaction is going to proceed to the right in order to make more product reactant until it comes back to a new equilibrium with the same equilibrium constant, by the way, but different equilibrium position, different equilibrium concentrations of products and reactants. So it's often shown this way as sort of a balance. Adding reactant will shift the reaction to the right to consume what you added. If you add product, that shifts the equilibrium to the left to consume what you added. If you remove reactant, that is going to shift the equilibrium to the left to replenish what you took away. Now it says remove reactant. Typically the way we remove reactants Sorry, that was a telemarketer calling my cell phone, which is of course illegal, but never mind that. I hate them all. Okay, so here we are. Now let's come back to where we were. It says removing a reactant. Now you don't actually go into the reaction vessel and pluck out reactant. The way we traditionally remove reaction components is by adding something that reacts with them. Okay, removing product or adding something that reacts with a product will shift the equilibrium to the right to make more product since you removed it. Now, this is a picture showing that if you add, we have H2, NH3, and N2 in equilibrium, and then of course N2 is just added at a certain time. That's just like the cartoon we did earlier where I threw in some extra nitrogen, And so that's why the purple line goes way up, straight up, because you added some. And then the concentration of N2 is going to decrease over time along with H2 because the reaction shifts to the right, and those are reactants, so they're going to go down in concentration, and NH3 is going to go up in concentration because the reaction shifts to the right. And then you establish a new equilibrium, right? So remember that another way of thinking about Le Chatelier's principle is that it's the relationship between Q and K. If you add a reaction component, that is going to change Q, and it is no longer equal to K, which means that you establish a new equilibrium where Q again becomes equal to K. And you'll notice that the H2, NH3, and N2 concentrations at our new equilibrium are not the same as they were before, right? They change concentration, but the K value stays the same. Now, solid-liquid reactants do not affect the equilibrium, and that is because they do not appear in the equilibrium expression. So here we have a reaction system where we have a little bit of calcium carbonate and a little bit of calcium oxide. Those are both solids. And then we have CO2 as a gas in equilibrium with these two solid reaction components. And so if you add in calcium carbonate, you'll notice that that's happened from the A and B. If you have different amounts of our solids, as long as there's still some solids left at equilibrium, then the partial pressure of CO2, you'll notice that based on the height of the mercury in the PCO2 in the little tube to the right, that is not any different. And so you still have the same concentration of gases. So Le Chatelier's principle is not relevant to solids or liquids in the equilibrium because they do not appear in the equilibrium expression. Now if we change the temperature, here we have an equilibrium established between the cobalt hexahydrate and cobalt chloride. One of them is pink and the other one is blue. This is related to this is just like the lab we did. So the hot water will shift the equilibrium to the blue side, the cobalt chloride side, and the cold temperature will shift it to the pink side. Okay, and this is related to the delta H of the reaction. And so this particular reaction is endothermic, which means heat is a reactant. And so at the hot bath, basically what it's doing is the temperature goes up and the reaction wants to shift in the endothermic direction in order to remove some of that temperature, right, to lower the temperature. And so it shifts to the right, which is the blue side. Another way to think about it is that in an endothermic reaction, heat is a reactant. So if you add heat, you're adding a reactant, it's going to shift to the right. If you remove heat by making it cold, then it's going to want to shift to the left to replenish what you took away. So you consider heat a reaction component. Most people prefer to think about it that way. So this is another example of the effect of temperature, right? In the cold N2O4, the colorless gas is preferred, and in the hot water bath, the brown gas NO2 is preferred, and that is because the reaction, as you see it here, is endothermic. Delta H is positive. And so again, if it's endothermic, then heat is a reactant. It goes in on the left, and so the cold temperature, you're removing heat, it's going to shift to the left. And if you increase the temperature, you're adding heat, you're adding a reactant, and it's going to shift to the right. So let's label those. Cold is on the left, room temperature is in the middle, and the hot water bath is on the right. We did this lab in class. Actually, this is the one you did in the hood. This is another picture of it that I got from somewhere, Google or Wikipedia, and I just thought it looked cool, so I put it in there too. So here we have adding a reaction component shifts the reaction whatever direction consumes what was added. Removing a reaction component shifts the direction whatever direction replenishes what was removed. And then we can add temperature. Raising the temperature shifts the reaction in the endothermic direction to remove heat and lower the temperature. Lowering the temperature shifts the reaction in the exothermic direction to add heat and raise the temperature. So you're basically, the reaction is just going to shift in whatever direction undoes what you've done. Now finally, pressure is the last one I wanted to consider. If we took this equilibrium N2O4 and NO2, we can use how dark brown the system is as a measure of how much NO2 we have compared to the colorless N2O4. So if we cram this reaction into a tiny container, that's going to have high pressure, right? And so this high pressure situation on the left flask, that's going to favor the fewer moles of gas, and so it's going to favor the colorless N2O4. Now, if we all of a sudden increase the volume, like we're showing here, that lowers the pressure, and the system is going to want to shift to make more gas molecules because that's the only way it can influence the pressure. And so it shifts to the right to make more NO2 so that it can increase the pressure on its own, and that eliminates that volume increase, or that alleviates the volume. So here's another picture of it where we have more N2O4 on the left and we have more NO2 on the right, and this is just trying to show you the effect if we put molecule glasses on instead. And that's because PV equals nRT, right? The system can only influence the pressure by increasing moles of gas. And so on the right we have 2 moles of gas. That would be a higher pressure than on the left, which is 1 mole of gas. Higher pressure favors fewer gas particles. That's the reactant side in this particular reaction. And lower pressure favors more gas particles, which is the product side in this reaction. So there's 2 moles of gas on the right, 1 mole of gas on the left. Now here we have another equilibrium. So this is a picture from your book where you have 1 mole of N2 and 3 moles of hydrogen on the left. That's 4 moles of gas altogether, and 2 moles of ammonia, which is 2 moles of gas on the right. Now you can see here in the bottom when you go from A to B, okay, so we increase the pressure by decreasing the volume, and so that's going to cause it to want to shift to the right because there are 2 moles of gas on the right and there are 4 moles of gas on the left. And so the net reaction shifts to the right and forms more NH3, right? Now if we add in our last couple of things here, increasing the pressure by decreasing the volume causes the reaction to shift in whatever direction has fewer moles of gas. This lowers N to lower P. And finally, decreasing the pressure or increasing the volume causes the reaction to shift in whichever direction has more moles of gas. That would increase moles of gas, and that would increase P according to the ideal gas law. Now, the last thing about Le Chatelier's principle is that catalysts do not affect the equilibrium position or the equilibrium constant. And the reason for that is because the catalyzed reaction, the red line, decreases the activation energy, and you can see that with that delta EA, that green arrow. And so the forward energy of activation and the reverse energy of activation, you have enhanced the rate by lowering EA, and the effect is the same for both the forward and the reverse direction reaction. Now, because the equilibrium is when the forward and the reverse rates are equal, then that means that if the forward reaction is influenced the same as the reverse reaction, then there is no effect on the equilibrium position or the equilibrium constant by the presence of a catalyst. So the last thing here, catalysts do not affect the equilibrium position, and that's the last piece of Le Chatelier's principle. And this is the last thing, is our little my little cartoon with the seesaw, which is sort of the balance on the fulcrum that we've been using to portray Le Chatelier's principle. Here's our fish, and he's accidentally ejected his fish friend from the fishbowl. It's very sad.